Okay, well, thank you for enthusiastically continuing to invest your time into the project. I'm looking forward with great enthusiasm about our Wednesday meeting and project, and with a little less enthusiasm for today, but we need to come over some material. So what would be the, I don't know what is the title, but I know where I want to go. So we are in the part of this course dealing with thermodynamics as empirical theory without much of microscopic things. So some macroscopic observables of like collection of lots of molecules can be deducted without knowing details of the structure. And thermodynamics is not a science. It's engineering for making heat machines. So what have we done in the past lectures where we did actual thermodynamics? So we agreed that the heat machine makes this diamond cycle with isotherm and adiabatic. And we agreed that for isotherm, it's okay to believe that PV equals constant, and for adiabatic, PV to the power gamma is constant. And this gamma depends on number of degrees of freedom in the gas, like what to put in your steam engine, like actual steam of water, or steam of alcohol, or maybe something exotic. So there is a goal on this path that I'm going to announce, and there are some skipped parts of material that I'm going to return back. So in today's meeting, I will borrow some material from not delivered parts, and then we'll come over the meeting. So the question that probably we will answer by the end of next Monday, if we spend Wednesday for the projects, will be what happens if steam between rod and piston of your heat machine will start to condensate. Will it affect the efficiency and productivity of the steam machine engine? So what are your opinions? What would happen if like the conditions outside, would it like make it better, make it worse? Would it stop? Would it condense and evaporate back? So any opinions just for starting? Ichi? Well, is the question clear? So the heat machine is the stuff that we were discussing, like little rod and piston, right? Mass here, and here is the gas. We have a heat, right? What if during the cycles of this going up and down, the gas will start to condensate into the liquid? Is it critically bad, or it is okay? Yeah, but to which extent? Would it like damage the overall cycle, or is just slightly reduce efficiency? I don't know. We will answer next Monday. Any opinions?
I think it would probably damage the efficiency.
Okay. Sohi, any opinion on how the efficiency of the steam machine will be affected if you have condensation? The microphone is muted.
Sorry, I just joined, so
That's fine. That's fine. I also just joined. Do not worry. I like when people come later because then I do not feel obliged to come in time myself.
Yeah.
So when you were speaking about thermodynamics, we had this heat engine, right? When you put some fire stove and gas expands and pushes some mass up, and then we remove the stove, put it like in DUR, and it goes back, and then it repeats up and down and makes some work. So is it bad, or it is acceptable if you have a little bit of liquid right inside?
I think it would be bad.
It would be not the best scenario, but would it be like terribly bad, or it will just reduce efficiency like twice, but it is still the train will go forward?
Still works.
Yeah, it may work under some conditions, but there, if we think not like scientists but like engineers, we need to look ahead and predict possible shortcomings. So this is kind of, I wouldn't say long-term goal, but mid-term goal. Mid-term, not in a bad sense of any exams, like a goal for next Monday. And for today, I want to learn myself and consult with you and discuss the following thing. So if we are thinking empirically about the gas inside this between rod and piston, and our independent variables are yes.
Wouldn't the pressure be different though? Because the liquid would push like differently than a gas would. Like when you're compressing a liquid further versus compressing a gas further, because a gas could compress, but a liquid's already compressed. Wouldn't that change the like pressure response for like when you're trying to compress it, so it won't compress as much?
Crystal, you are absolutely correct. If the all gas will convert into liquid, it will not work, or it will be like infinitesimal efficiency. But what if two phases coexist? If part of the steam condensates, if there are like let me make a better image to avoid misconception. If we have just few drops of the liquid on the walls here and there, and there is a coexistence between gas and liquid. So it definitely will make analysis more complicated. We need to consider evaporation and condensation dynamically. But if we do not care about science and just need efficiency, it's like a little goal that we can pursue. And it will be not achievable by today, but we will create some foundations to answer this question next time. I hope. Okay, and thank you for questions. I really like the discussion style because I'm learning too, and it's investment of next years into next year. So what if the independent variables are volume and temperature of the gas in this container? So there is a question that we would try to address. What is the response of the pressure to temperature? Like if we change the mass here, if you change differently, if we heat the gas like by 1 Kelvin degree, would it, how stronger will it push the rod outside? So pressure as function of temperature. Is it possible? And some of you may immediately take the ideal gas, just take a derivative and start answering. But we are under constraints. We are playing the game where we do not know about microscopic nature of the material. So we want to do something empirical, something general. And second question, like when we are practicing adiabatic part of the cycle, the gas under certain pressure and temperature and volume expands. It pushes this mass outside. And by pushing it outside, the volume increases, pressure decreases, and temperature drops, right? So the question is, if we want to avoid temperature drop, how much firewood we should burn? Like how many pounds of firewood we should burn to keep temperature constant if the volume is increased by certain amount. So if you have change of volume and we want to keep temperature constant, what will be the amount of the heat that we communicate to the system? So it is like engineering question of 16th century. Like if you build ancient steam engine and you want to make it efficient economically, you want to count your expenses, like, or if it is like train. Have you seen the? Well, surely you did. Have you seen the steam trains? So, what there are like carts for passengers or for some load. There is a locomotion in front, and what is between them? When I was 3 or 4 years old, it was my question number one about trains. So between the compartments with passengers, like wagon with passengers, and actual locomotive with steam engine, what is in between?
The coal train.
Yes, coal train. So what is the supply of coal you need to take to the road if your piston will expand to a certain volume like each second, right? So this is the engineering question. I mean, we're not doing science. So two questions: amount of coal to burn and how pressure will change if we modify the temperature by a degree. So we're done with far goal, near goal, which is to find these two things. And we partially covered the input from our previous. No, do not call me. I will not answer. Whew. So we need to, well, I'm going to announce the answer so that we do not like go in the dark. So the equation I need to learn and to discuss is change of the internal energy in respect to volume on one side, and on another it is a change of pressure in respect to temperature. On one side, change of internal energy over volume, and then to keep dimensions correct, So how do I? There is a little task before we go into derivations and considerations. Like I don't know. I hope and believe you all have young, bright minds which use photographic memory for equations. I don't. So if I want to memorize this equation, so the internal energy dimension is energy or work, and energy is like volume times pressure. So if I make a derivative over volume, the dimension of this part will be same as pressure. So like having pressure here is okay. And if I have derivative of pressure over temperature, then to have dimensions of pressure, I need to put temperature here. It's not a derivation. It's only like a way how to memorize it. This analysis of dimension will not replace actual derivations. It's only one of the way. Okay, how you? So one of the way to like check if we memorize stuff well, and by exploring this equation in different limits, like constant volume or constant temperature, one can answer the questions we are interested in, like how much coal one needs to burn, or how much the pressure will change if we heat it up a little bit. Okay, so the goal is to get this equation derived. Are there any ideas where to start? Some of you were successful in undergraduate physical chemistry. Some of you were even carrying textbooks. So any ideas where to start and where to go? Like which input information can we use? If no answer is fine. I learned it on this weekend. So there.
Could we consider one of that since it's in the expansion that PV is constant, then treat something as a constant maybe, or?
Mm-hmm. And we also need the first law of thermodynamics that we didn't discuss and derive, but and we even didn't pronounce this name, but we need to consider a concept that increase of like external heat will be balanced by change of internal energy and external work, or heat and work are leading to change of internal energy. So these words do not scare you, right? Good. They shouldn't scare me as well. I think we also were defining the internal energy. So there is another.
What did you set U equal to? I'm sorry, I can't quite see it. U equals.
U equals PV over gamma minus 1.
Thank you.
Okay. So there is a piece of input that we need to borrow from the future in sense of our lectures or from textbooks or other materials. So borrow. And we can say that change of internal energy is balanced by heating and work, right? Energy, heat, and work. So we'll discuss it at some point. Just it's still more than enough time for this for the subject of thermodynamics. So maybe borrow number 1. Another statement to borrow from the future is what is the total work done onto the gas in the space between rod and piston. If we are practicing Carnot cycle in this axis, if we do this little curvilinear diamond, what is the total work if we do not consider heat and look only on the work? So
wouldn't the work just be 0 on the gas itself, not on the piston, but the gas?
well, the work can be derived as integral, right? And if you go one way, if you go the lower, it will be this area. Then if you go the upper side, it will be this area, right? And if you
So the work will just be the area of that.
Exactly. So if we are doing this cycle, then it will be the area inside this curvilinear diamond. So, and I'll pay tribute to my own laziness, and instead of going over each side of this stuff, I just put integral over the contour, which means like going the closed loop. Okay. So we are done with input. Borrow from future. And 32 minutes. Yeah, we're doing good in time. I think we'll overuse. So next thing in the plan is to draw a couple of figures. So this one was figure 1. And now I'm going to say very trivial things, so trivial that I'm even hesitant and shy to say it. But they needed just a little foundation for the next step. So I apologize for declaring trivial stuff. So suppose we have function f of 2 variables x and y. Okay. So the function f will go out of plane, and the axis will be x and y. Okay. And I'm going to consider 2 points, x and x plus delta x, and then y and y plus delta y. And the x, y, f, x plus delta x, y plus delta y. So the trivial question that I'm going to address is to how to express increment of the function along this path. Anyone wants to help me? It's fine if you don't, but if so it's trivial, right? So you take the increment is value at final point minus value at initial point, right? No tricks, no lie. But mathematically, I am always have a freedom to add and subtract the same number. So if I like minus c plus c, nothing will change. So can you guess what will be the c? And what I know it is not a legal question, but guess what I'm thinking about. So let me open cards. Later on, we will need to practice partial derivatives, right? So we need multivariational calculus, right? And so we need to see how function responds to change of two variables simultaneously, or one variable is if another one is kept constant. And this instrument, or this set of tools for multivariable calculus, deals with taking increments over either one or another dimension. It doesn't simultaneously go into both directions at one step, right? So we need to dissect this little short vector on two long vector and two shorter vectors. Okay? So either this and that, or this and that. Okay, and this can be done without breaking any rigor, just by adding and subtracting appropriate constant. So if I want to go along, like if this is my 1, 2, and 3, if I want to go along y first, then this will be arrow from 1 to 2. And then, just to be mathematically correct, I need to subtract the same number. I just will try to condense calligraphy. So in the lower line, we have the same x, but changing y, right? In the upper line, we have the same y, but we are changing x. So this one will be, this is the main reason why we are meeting in class, not in Zoom. I don't know how to mimic this sound, this clicking sound. So this will be from 2 to 3. Okay. So I hope you accept my apologies for bringing up this trivial thing, but we will be basing some very simple derivations on it. So now, for this statement, can we practice the regular calculus and give some fancy names to these two subtractions? If we forget about multivariable, but just look on response of a function into change in one of the variables. What is that? Partial. Right. Everyone agrees, right? So delta f for the path 1, 2, 2 to 3, we are changing x and keeping y unchanged, right? So it is partial f over x times delta x. And the second part will be here we have x unchanged, but y is changing, right? So it will be partial f over dy times delta y. And this will be path from point 1 to point 2. Right?
Question.
Yes?
Do you not have to put, like when we were just talking about the informal stuff like this, do you not do partial f over partial x with like a subscript y?
Yes, it is a very good suggestion. Thank you, John. So here we are telling that y is kept constant, and here we tell that x is kept constant. So in some sort it is redundant duplication, but it's better to have redundancy rather than making errors. And in the thermodynamics, people always like placing this comment of what is kept constant. Okay, so where we are now? We are done with figure number 2, and we are done with multi-variable derivatives. Okay, I'm going to erase everything except our answer. That will serve as a little cheat sheet. Like if I arrive to this equation, it will be success. If I fail, it will be failure. Yeah. So what is our function right now of interest? I do not have any argument why, but our function of interest will be internal energy. What will be our variables instead of x and y? I also do not have arguments, but they will be temperature and volume. But this is kind of free volus selection, may be comfortable to solve engineering problems, but one can there is a way to replace some variables and select independent variables in a different set, like temperature and pressure instead of temperature and volume. So our function is u. It depends on temperature and volume, and we need to consider increment in this internal energy. Okay? So we will just practice the same multivariable stuff. So change along the volume axis and change along the temperature axis. On one hand. On another hand, we have a stuff that we did borrow from the future. That change of internal energy is heat that we communicated by burning coal under the pot. minus what? Pressure times pressure times change of volume. So we're going to compare two equations, and we will do it in 2 minutes. So first, limit if the volume is constant, and this is isochoric. If you look into like your undergraduate things, right? Crystal, not changing volume in some ancient languages is isochoric, right? But here it is also an approximate way to mimic adiabatic when the curve is very sharp and volume changes slightly. So what do we have in this limit? We do not have change. We do not have work, right? And then we can make these two things equal, right? So we'll be and then we can just divide both left and right on delta t, and define it how much all needs to be burned to, or if you change it by its proportion between heat and change of temperature, right? Or right. So is there a name for this stuff? How energy changes in respect to temperature? And why I do not like thermodynamics, because there are so many different symbols and slight deviations for basically the same units for the same variable. Like there are a lot of symbols which have dimension of energy, but generally derivative of energy in respect to temperature. What? Capacity. Yes, heat capacity, right? Any yes, no. Okay, everyone agrees. And it is a heat capacity with constant volume. Okay. Can I delete this little panel? So in second limit, we will have temperature equal constant. And on one hand, some terms in these equations will drop. On another hand, it corresponds to this engineering question of efficiency of the heat machine, like how much additional coal we need to burn to keep the temperature unchanged. Like because it will cool down through expansion of the volume of the engine. So I didn't lie, but I miss one more thing that we may we need to use today, and that we will derive in the future. So there is another borrow from future. So that work can be expressed in terms of heat and temperature. So this is also borrowed from the future, but we will discuss it, and it may partially relate to our project. Not literally, because our project is quite far from thermodynamics, or thermodynamics is quite far from the project, but here is one of the point of interfacing. So there is a little, I wouldn't say trick, I wouldn't say it is intellectual step, but we need to tell what will be the work over cycle or contribution to the work if the amplitude of motion for the rod and piston is infinitesimal. If it is like if you looking to buy a truck or a Jeep, it tells like 4-liter or 8-liter engine, which is not very economic but more powerful. And now we need to look for something very economic where the displacement will be really small. So there, and it will be a trick. So how to process work, how to treat work if change of volume tends to 0. So first we have our curvilinear diamond. If this change in volume delta V is really small, then it is okay to neglect the curvature. So it is a big sin on a big displacements to change function 1 over V to just linear of V. But if it is a small displacement, we can take it as parallelogram or this all lines are straight. And now another trick. So if we add and subtract areas of these triangles A and B, like subtract B prime here and add B here, then subtract A prime here and add A here, which have the same areas. Then we will identify that the area of the square with 90 degrees angles and area of this black diamond are equivalent. And in this approximation of the infinitesimal increment of the volume, one can tell that the small increment of work is just a change in delta P times delta V, just in rectangular coordinates. On the long range changes, it will not work, but for short range changes, it does. So volume is changing during isothermic, pressure is changing during the adiabatic. Okay. Figure 3 and with 2 limits. So the next thing I'm going to practice is to express the infinitesimal change of the work here and there from different angles. So I will just do several lines and compare these equations and put them together. And by doing so, we should arrive to the target equation, and it will allow us to discuss two things: how pressure changes with temperature, and how much coal one needs to burn in order to keep the temperature in this gas container the same. So I'm going to erase this area and keep other things as a cheat. So on one hand, we have this change contributed by heat, change in temperature, and work are balanced. Second thing, I will admit I borrowed it from the textbook, and it will look absolutely the same. So I will just rewrite this equation, but speak about it with different language, with different words. So we'll write this change in relative change in temperature times heat that we contributed, and here we can tell that when we contribute heat, we do not change the volume. and on other side we can so this looks like alchemy to me. I do not like the style, but it is the weakest, logically weakest part. So in some sort, this should be related to adiabatic, and this should be no, but they should correspond to different sides of the overall cycle. And now there is a logical, not logical. There is just mathematical trick. So the expressions, any mathematical expression can be divided and multiplied by the same factor, right? So what if I take the whole equation and divide left and right by delta v, multiply left and right by t, and divide left and right by delta t. So no one forbids me to do so.
There's a delta t over t, the previous equation.
Yeah, thank you. John, password. So if we cancel whatever can be cancelled and consider that these infinitesimal increments are treated as a derivative in the limit of the small thing, then we can treat it as change of the heat that one contributes from outside. Let me check. I may screw up something. Let me double check with my cheat sheet, and I will delete it from the recordings. Now it makes sense. Okay. And what? How do I differ in the last equation from the previous one? What is different? So
DQ instead of
yes,
V.
we have Q instead of U. We have minus P here. So what are the okay? One more change. Whew. Now everything is logical, and I'm confident that. So I just multiplied left and right by delta V. So through this little strange derivation, we got that how the amount of heat changes if we modify volume of a piston by certain displacement. And now we are bringing this several pieces together by bringing in the statement that change of internal energy is change in heat minus work. That later we will connect to the first principle of thermodynamics. So internal energy, heat, and work. And the only remaining thing is to plug in this change of heat into this balance between internal energy, work, and heat. And the very last step is to apply derivative, right? If we divide left and right by delta V, we will obtain what needs to be. So du dv. So we did three forms of the same, and we included the two terms of internal energy, and then we divided everything by change of the volume. So we arrived to the equation that we were planning to arrive, and now we need to interpret it a little bit. So if the volume is not changing, then first term drops. So internal energy is not changing, and then we can rewrite it as pressure equals to temperature, and the proportionality coefficient is this derivative, right? And if we have change in temperature constant, then it gives the amount of coal to burn to keep the temperature. Questions, please. There are opinions that equations like this is the core part of thermodynamics. So look at the simultaneous change of several variables. And in here, we didn't import any information about structure of material. So it's all phenomenological, and it was possible to do, and it was done like 200 years ago, before any knowledge about structure of molecules. This phenomenological approach, when functions are well defined and can be explored in the infinitesimal increment, can be also expanded to the situations away from regular regimes. So what would be a plan for next Monday is to extrapolate this equation to the situation when the gas condenses or evaporates, when two phases of the material coexist in one chamber, and to attempt to make conclusions about the efficiency of the heat engine in such situation, when the steam condenses inside between rod and piston. What else do we miss? What else we did bore, and what else needs to be brought in for thermodynamics part of the class? So this condensation in rod and piston, and then things that we did borrow. So first, principle of thermodynamics, and principles of thermodynamics, and also the work expressed in terms of heat and temperature, which brings us to definition of entropy. So at least three things needs to be added to make maybe not fully complete, but balanced picture of thermodynamics. The entropy and work in terms of heat and temperature, the principles of thermodynamics, and efficiency of the heat machines, including the case when two phases coexist. Okay. Any protests or questions are welcome, but I think we are done, and we didn't waste too far of your time. Yelling is natural reaction to this material. Bias, any questions?
No, I'm good. Thank you so much.
Yeah, thank you. Sahi? Any?
I have no question today.
Okay, yeah, thank you.
Projects on Wednesday.
Yes, yes, and basically everyone selected. Maybe Tyler, we need to exchange a couple of emails because you were not voting, and the only subject for projects which is left is probably the most complicated. So we need to chat if you are happy to accept it, or we need to do some rearrangements. But I have some idea how to make everyone happy and not very busy.
All right, sounds good.
Okay, so I'm going to disconnect unless anyone stops me. More questions 1, more questions 2, more questions 3. Done.
Thank you.
Thank you.